and the other has radius r2. But what does that tell you about r2?
2 times R1.
2r1, correct? Is that cool? And I want you to compare the accelerations at each. Well, what kind of motion are these in? Are these in circular motion? So what kind of acceleration do they have if they're in circular motion? Centripetal acceleration, true? So how do you calculate the centripetal acceleration? V squared over r. So I want to figure out if I can get v squared over r. Well, why is either of these even in orbit? Is there a gravitational force on them? There is, right? So I know that they're in circular motion, so centripetal force has to be equal to the gravitational force. This is one of your starting places. This is where you look and you're like, this is something I want to understand. Centripetal force is mv squared over r. Gravitational force is gmm all over r squared. Where in this case, r is your center to center distance. Cool? What I'm noticing right away though is these m's, this is the m of the orbiting body, this is also the m of the orbiting body, so those can cancel. And I'm left with v squared over r is equal to gm over r squared. But isn't this what I'm looking for? See that? So now I have a way to express that. I can say that the acceleration for planet 1 is going to be equal to gm all over r1 squared. Is that cool? And acceleration for planet 2 is equal to gm all over, well, what do I have here? It's 2r1 all squared. So you see what I did there is instead of writing r2, I used our understanding that r1 or r2 is 2r1 and I put it in there. This is where some people trip up a little bit, is they just want to put 2r and then just square the r. But you doubled the radius, and so whatever your radius is, that whole thing gets squared. So it's 2r all squared. Okay? So how does it write this? It has it in terms of A2. Do you guys see that there? All right, so if I look at this, I see that A1 is equal to gm over r1 squared, and A2 is equal to, basically, it's gm over 4r1 squared. Now, this is an algebra trick that I don't know if it's obvious to you guys or not. Okay, I don't know if it's obvious to you guys or not, but you see how A1 is equal to gm over r squared? So when I look at A2, I notice this is a quarter times gm over r1 squared, which is A1. You see how I just took this whole term and I substituted it in here? You guys with me on that? So A2 is equal to a quarter of A1. Is that an answer?
Yeah.
Boom. Nailed it.
I put the opposite. I said 4 times.
It happens. 7. Was that just 7?
8.
The radius of the Earth is probably 6,000 kilometers. The acceleration of an astronaut in a perfectly circular orbit 300 kilometers above the Earth would most nearly be. This is a use your brain question, not a calculate question. So if we look at the Earth, whoa, I got it looks like over there. Okay, so let's look at the Earth here. And it says that this is 6,000 kilometers. Well, what percentage of 6,000 is 300.
Half. Oh, 300. I read that as 3,000.
I gotcha. All right, what percentage is that?
1 over time.
I mean, is it a lot or a little,
Little.
is the question. Right, it's a little. That means that the satellites are actually, 300, it's 5%, right? There are 2,300s in 6,000. You with me? So it's 1/20th of that. So satellites are here. So if I'm talking about the acceleration, it's gm over r squared. Remember, r is the center to center distance. So I'm going to compare my center to center distance. At the surface, there's my r, and my g value is equal to 10. So you tell me this. Is this a lot more or a little bit more? Is this new r value a lot more or just a little bit more?
Just a little bit more.
Just a little bit more. So as r gets bigger, g goes down, true? But did it get a lot bigger or a little bit bigger?
A little bit bigger.
Just a little bit bigger. So what happened to g?
11.
It just got a little bit smaller. As r goes up, g goes down. So I have the amount, yeah.
So I understand how you explain it, like estimating it, because I did the same thing and I got it. But every time I tried to work it out, I got a number that was like way off. You show like what to plug in, like.
If you want to plug and chug it, which is a great way to go, we can do that. So, big G value, 6.67 times 10 to the negative 11. The mass here, 5.98 times 10 to the 24. Now, let's calculate it right here. All right? So what is my R value? Well, I'm going to have to go the radius of the Earth, which is 6.37 times 10 to the 6th, plus, now, here's the deal. It said that this radius here is 6,000 kilometers, so it's 6,000 kilometers, so they're talking about 6 million meters. They're saying this distance right here is 300 kilometers.
300,000.
Which is 1, 2, 3, 4, 5. So it was tricky because it's giving you stuff in kilometers, but we don't get to work in kilometers, we have to work in meters.
I've got to read these questions more closely.
Uh, 9, 10, 11. This is a satellite X moves around the Earth in a circular orbit of radius r. Satellite Y is also in circular orbit around the Earth, and it completes one orbit for every 8 orbits completed by satellite X. What is the orbital radius of the satellite? Yikes! All right. This is not obvious as to what to do here. Okay, this one is not obvious as to what to do. So let's put the Earth back up here. So here's our Earth. And we know there's a satellite in orbit, cruising around. It's very happy to be cruising around. Okay? Now, yesterday, we looked at Kepler's third law, and we said that for anything that's orbiting one central body, so in this case, it's the Earth, we know that the t squared over r cubed ratio is constant. Okay? That was Kepler's third law. We talked about that yesterday. It may not have been obvious in the moment. What that means is that I'm going to know that the t squared over r cubed for x has to be equal to the t squared over r cubed for y. The hardest part about this problem is it says that y completes one orbit for every 8 orbits completed by satellite X. So what does that mean about Tx and Ty? How are they related?
One is 8 and one is,
One is 8 times the other. I just don't know which it is. Is Tx 8 times? So T is the time it takes to go around. That's the period. So let's try to think about it here. If y completes one orbit for every 8 orbits completed by x, which one's going faster?
the first one, the X.
So x does 8 when y does 1.
Oh, Y is going fast.
Okay? X does 8 when y does 1. So it's going faster, but that's not what we're looking for. We're actually looking for the times. So if x is going faster, what should be true about the time it takes for him to go around once?
Lower.
Should be smaller. If you're going faster, then it's less time. Okay? So what does that mean? So the time for x is less than the time for y?
So 8th, yeah.
Buy that or no?
Could you also go on about it like the G equals GM over R squared way?
No. So this is, you have to understand that it's asking about 2 objects orbiting one central body, and it's asking you to compare the time it takes for them to go around and the distance. So if this is true now, then we can make this happen. So I know that t squared x, so I'll say, hold on. I'm going to get rid of the fraction. So 8tx is equal to ty. Okay, cool. So I have t squared x over radius x cubed is equal to, I'm going to substitute this in, 8tx squared over radius y cubed. Now, here, I'm going to cross multiply and try to simplify it a little bit. So I end up with ry cubed times tx squared is equal to rx cubed times 64 tx squared. You guys with me there? So, I can see that the tx squares go away, and so I end up with ry cubed is equal to 64rx cubed, and I have to square root both sides. So ry is equal to root 64rx.
Wait, you mean cube root or?
Oh, I didn't mean cube root. Okay, and what's a cube root of 64? It's 4. That is a hard one. Okay, that is a hard one because you have to know 2 things. You have to know what Kepler's third law says about any object, any 2 objects orbiting one central body, and then I thought this was really challenging. Like makes 8 times. I don't know. That was 11. Let's do 12. All right, 12 says, I thought today was the day I was supposed to wear my thing. I'll be wearing this again tomorrow. I know, but like they wanted to like take our pictures. I know. It's not my fault. Oh, this is good. Refer to a ball that is tossed straight up from the surface of a small spherical asteroid with no atmosphere. The ball rises to a height equal to the asteroid's radius and then falls straight down toward the surface of the asteroid. What force, if any, acts on the ball while it's on its way up? Now, if I'm on the surface of the Earth, okay? If I'm on the surface of the Earth here, and I throw a ball up, the ball goes up and comes down. And no matter where it is, if I draw the force diagram, what does the force diagram always look like? It just looks like mg. Near the surface of the Earth, the force on any object is constant. And the reason it's constant is because you're so far away from the center. Because the actual force here is Gmm all over d squared. This time we're just using the generic distance idea. And any distance above the surface you are is small in comparison to the distance to the center. Again, this distance here is 6 million meters. So a couple meters off the ground doesn't add to the 6 million. Does that make sense? But if you are on a small spherical asteroid, and now you're going to throw your ball, and the height of your ball is equal to basically another radius.
Oh, it should be half of
Is the force going to change?
Uh-huh.
It is absolutely going to change. Because the fact that you are now far enough that Gmm all over d squared, this d is basically going to be twice the radius. So the question is, what forces act on the ball while it's on the way up? Okay. It says only a decreasing gravitational force that acts downward. So it's on the way up. So as it's on the way up, it's getting farther away. What's happening to the force? It's getting less. So I actually think A is the answer, but let's look at the other ones too. Is there an increasing gravitational force? No, because it's getting farther when it's on the way up. If the question said on the way down, that would be a good answer. Is it a constant force? No, because you're far enough from the center that the distance matters. This one says both a constant gravitational force that acts downward and a decreasing force that acts upward. That's because students think that when you throw a ball upward, the force from your throw stays with the ball and decreases over time. But we know that as soon as you let the ball go, you can't. The force from the throw is gone. And this is something we talked about here. It says no force is acting on the ball. Kids will think this because if there's no atmosphere, then they think no force. But what do we know? That's not true, right? Right? It's the gravitational force. So this one, A for sure. That was 12. Let's do 13. Oh, I like this one. Same ball. We want to know what is the acceleration value right here.
Would it not be zero like it is on a when you throw it up and
It's not. When you get to your path here, your velocity is equal to 0, but your acceleration is still,
negative 10 meters?
right?
Yeah.
When you throw a ball straight upward, it's accelerating down the whole time. Even at the top, the velocity is 0, but the acceleration is still negative 10. True? So basically what they're asking for is calculate the g value. Well, we learned earlier today, this Gmm all over r squared. True? Now, this r here, okay, this r here is whatever distance it is from the center. So in this case in particular, the g value would be equal to gmm all over 2r squared, where this is at the surface, this is at its maximum height that is twice the radius. So we're going to compare these two. Since you got 1 radii off the surface, your actual distance from the center is 2r. So I put 2r there in the bottom. But, you see how it's squared? So how does the acceleration due to gravity at this height here compare to the acceleration due to gravity at the surface? Since you went twice as far, your gravitational value is 1/4. That's an inverse square model. So the acceleration is, or the path is at its maximum value for the ball's flight. No, it decreases over time. Equal to the acceleration of the surface. That's not true. Equal to 1/2 the acceleration of the surface. It's twice the distance, but it's an inverse square law. Equal to 1/4 the acceleration of the surface, of course. And then the sucker answer is 0, right?
Yeah.
There's always a sucker answer. A satellite M moves in circular orbit with radius r at a constant speed v. True statements about the satellite include which of the following? Ooh. I like this one. So we got a satellite here, mass m, true, speed v, radius r. I like it. Is its angular speed v over r? Yeah. It's an object going in a circle. For any object going in a circle, we know that v is equal to omega r. True? So if you want to calculate its angular speed, well, it's going to be v over r. That makes sense to me. Right? Its tangential acceleration is 0. Yeah, that makes sense. If it had tangential acceleration that was tangent, what would be happening to the speed? It would either be increasing or decreasing, right? You can have centripetal or radial acceleration, you have to if you're going in a circle. But if you have tangential acceleration, you're either speeding up if it's in the same direction as the velocity, or slowing down if it's tangential. So I think the tangential acceleration is 0 because the speed is constant. The magnitude of the centripetal acceleration is constant. That would be true also, because the centripetal acceleration value is equal to v squared over r. And it has a constant speed at a constant radius, so even though the direction of this would be changing, I think the value is constant. So I'm going to say all three. 1, 2, and 3.